Hello, this is Yashwin. In this video, I'll be solving paper 4, variant 1, May June 2020, 0625 Physics. Starting with question number 1, an aeroplane of mass 2.5 into 10 to the power of 5 kg lands with a speed of 62 meters per second on a horizontal runway at time 0 seconds. The aeroplane decelerates uniformly as it travels along the runway in a straight line until it reaches a speed of 6 meters at time 35 seconds. A. Calculate the deceleration of the airplane in 35 seconds after it lands. Alright. Deceleration is just negative acceleration, so it has the same formula, which is final velocity minus initial velocity divided by the time taken, and that is 6 minus 62 divided by 35, which is equal to 56 divided by 35, and the answer is 1.6 meters per second square. 2. The resultant force acting on the aeroplane as it decelerates. So force is equal to mass into acceleration, which is given in the question as 2.5 into 10 to the power of 5 kilograms into acceleration calculated is 1.6, and that is equal to 4 into 10 to the power of 5 newtons. The momentum of the airplane when its speed is 6 meters. So momentum is equal to mass into velocity, which is equal to 2.5 into 10 to the power of 5 multiplied by 6, and that is 1.5 into 10 to the power of 6 kg meter per second. B. At time 35 seconds, the aeroplane stops decelerating and it moves along the runway at a constant speed of 6 meters per second for a further 15 seconds. On figure 1.1, sketch the shape of the graph for the distance traveled by the aeroplane along the runway between time 0 and 50 seconds. You are not required to calculate distance values. So, in the first part of the question, it says that it decelerates uniformly for 35 seconds, which means the graph is going to be somewhat like this, and then it stops decelerating and continues at a constant speed for a further 15 seconds, which mean from 35 to 50 seconds it's going to be a straight line, and that's it. C. As the aeroplane decelerates, its kinetic energy decreases. Suggest what happens to the energy. So I'd say it's converted to thermal energy. Question number 2, figure 2.1 is the extension load graph for a light spring S. A. State the range of loads for which S obeys Hooke's law. So basically the range where the graph is a straight line. This is where it starts deforming. So this is the range from 0 to 8. B. Using information from figure 2.1, determine the spring constant K of spring X. So this equation we're supposed to be using over here is force is equal to constant multiplied by the extension, which should mean constant is equal to force divided by extension. So the values to be used over here should be the values which come under the straight line of the graph and not the curve, because we want them to be following the Hooke's law. So the force value I'm going to be using is 8, and if I drag it back to the y-axis, this gives the extension value as 15. So I have force 8 newtons divided by 15, which gives the answer as 0.53 Newton per centimeter. C. a second spring identical to spring S is attached to spring S, and that basically means they have they have the same spring constant values which we calculated in the earlier part. The two springs are attached to a rod as shown in figure 2.2. A load of 4 newtons is suspended from the bottom of spring S. Arrangement is in equilibrium. 1. State the name of the form of energy stored in the two springs when they are stretched. So this is elastic potential energy. 2. Determine the extension of the arrangement in figure 2.2. So here we're supposed to be calculating the extensions separately since they're attached like so, and that means extension is equal to force over spring constant, which is 4 over 0.54 plus the second one as well, which is 4 over 0.54 since they are identical springs, and that gives the answer as 14.8. Rounding it to two significant figures gives the answer as 15 centimeters. 3. The load is carefully increased to 6 newtons in total. Calculate the distance moved by the load to the new equilibrium position as the load increases from 4 newtons to 6 newtons. Alright, so 4 newtons had the extension as 5, 15 centimeters, sorry. And when it increases from 4 to 6, basically it's increasing by half of 4. And that means if you subtract 4 from 6, you're left with 2, which is half of 4, which also means that the extension should be half of that which we had earlier, and that is equal to 7.5 centimeters. Question number 3, figure 3.1 shows gas trapped in the sealed end of a tube by a dense liquid. Alright, so here only atmospheric pressure is being applied, but over here the pressure on this level is supposed to be the pressure of the gas trapped over here, and since they are both at the same level, that indicates the fact that the pressure of the gas trapped in this sealed end is equal to atmospheric pressure. The scale marked on the sealed end of the tube is calibrated to read the volume of gas trapped above the liquid surface. Figure 3.1 shows that initially the volume V1 of the gas is 60 centimeter cube. The pressure of the atmosphere is 1 into 10 to the power of 5 pascals. A. State how figure 3.1 shows that the pressure of the trapped gas is equal to the pressure of the atmosphere. So as I mentioned earlier, pressure at same depth is equal, and that means the pressure over here, depth, and the depth over here is same, and basically that is indicated by the levels of these two surfaces of the liquid. As they are equal, that means the pressure is same. B. Explain in terms of momentum of its molecules why the trapped gas exerts a pressure on the walls of the tube. So here we have a bit of a given answer. Whenever you are supposed to be explaining pressure in terms of momentum, keep in mind that pressure is equal to force upon area, and this force is equal to change in a rate of change in momentum. Force is equal to mb minus mu divided by t. So you're supposed to be starting with the explanation of change in momentum, which causes change in force, which exerts pressure on the walls of the container. The first given statement should always be that molecules collide with the walls of the containers. And then, due to this collision, their velocity changes, which also results in the change of momentum. And due to this change of momentum, force is exerted. As pressure is equal to force divided by area. C. More of the dense liquid is poured into the open end of the tube. The level of the liquid surface in both the sealed and the open ends of the tube rises as shown in figure 3.2. The temperature of the trapped gas and the atmospheric pressure both remain constant. 1. In the sealed end of the tube, the volume V2 of the trapped gas is 50 cm3. In the open end of the tube, the liquid surface is 15 centimeters above the new level in the sealed tube. Calculate the pressure P2 of the trapped gas. Alright, so P1 V1 is equal to P2 V2 according to Boyle's law, since temperature is constant over here. We're supposed to be calculating P2. It should be equal to P1 V1 divided by V2. So P1, which was initially the pressure of the gas trapped, was equal to atmospheric pressure, and that is 1 into 10 to the power of 5 multiplied by the volume initially was 60 centimeters cube, and it has now decreased to the second volume, which is 50 centimeters, and so the second pressure is 1.2 into 10 to the power of 5 pascals. So this should be higher than the atmospheric pressure, as the volume is decreasing, and volume and pressure according to Boyle's law are inversely proportional. To calculate the density of the liquid in the tube. So pressure in a liquid is equal to density into gravity into height, which should mean density is pressure divided by gravity into height. So pressure of the liquid is not given. However, P2 over here means at this level, the pressure in the liquid should be equal, which is basically pressure due to 15 centimeters and atmospheric pressure, which is 1 into 10 to the power of 5. So if we subtract the atmospheric pressure from a 1.2 into 10 to the power of 5, we're only left with pressure due to this liquid, and that means pressure is equal to 1.2 into 10 to the power of 5 minus atmospheric pressure, and that is equal to 20,000. So density is equal to pressure divided by gravity into height. I'll convert 15 centimeters to meters, which would be equal to 0.15 meters. And so the answer is 1333.33, which is a recurring figure. So 1.3 into 10 to the power of 4 kg per meter cube. Question number 4. Water has a specific heat capacity of 4200 joules per kg degree Celsius and a boiling point of 100 degrees Celsius. A. State what is meant by boiling point. B. A mass of 0.3 kgs of water at its boiling point is poured into a copper container which is initially at 11 degrees Celsius. After a few seconds, the temperature of the container and the water are both 95 degrees Celsius. So the change in temperature of water is from its boiling point to 95 degrees Celsius, and change in temperature of copper container is from 11 degrees Celsius to 95 degrees Celsius. 1. Calculate the energy transferred from the water. So specific heat capacity is energy over mass. into change in temperature, which means energy should be equal to specific heat capacity into mass into change in temperature. The change in temperature of water is from boiling point to 95 degrees Celsius, which is equal to 5. So specific heat capacity given in the question is 4200 multiplied by the mass 0.3 into change in temperature is 5 degrees Celsius, which gives the answer as 6300 joules. This is the energy transferred from water to the copper container. To calculate the thermal capacity of the copper container, thermal capacity is basically energy divided by change in temperature. There's no mass over here. So that is equal to energy obtained by the copper container is equal to energy transferred from the water, which is 6300, divided by the change in temperature of the container was from 11 to 95 degrees Celsius. So 95 minus 11 is equal to 84. So 6300 divided by 84 is equal to 75 joules per degree Celsius. 3. Water from the container evaporates at the and the temperature of the remaining water decreases slowly. Explain in terms of molecules why evaporation causes the temperature of remaining water to decrease. Alright. So energy is required for the water molecules at the surface to break their bonds from the water in the container, and after they have obtained that energy and broken their bonds, they can then escape from the surface and into the air in the form of water vapors. So the molecules which are left behind have less energy, and so the temperature decreases. Over here I'll start by energy. Question number 5. The distance between the center of a thin converging lens and each principal focus is 5 centimeters. A. Describe what is meant by the term principal focus for a thin converging lens. So we're supposed to be writing the definition over here, which is B. The lens is used as a magnifying glass to produce an image I of an object O. 1. Underline the terms that describe the nature of the image produced by a magnifying glass. So of course it's going to be enlarged and virtual along with upright. 2. Figure 5.1 is a full-scale diagram of the lens and the image. 1. On figure 5.1, mark both principal focus and label each of them F. By drawing on figure 5.1, find the position of object O and add object O to the diagram. Since this is supposed to be a... Alright, I'll first start by marking the principal focus on both sides. So each half of the unit is equal to 1 centimeter, which means two of them are 2, 4, and 5 over here. So I have F over here. Similarly, 5 boxes away from the center is F on left as well. Now I'll start drawing the rays so that I can identify the position of the object. So first off, the one of the lines is going to be passing from the top of the image through the center of the lens. The second line, since this is a magnifying lens, it would be an imaginary line on one of the sides, and it would then pass through the principal focus. So from the top of the image, an imaginary line to the lens, and then it's going to be passing through the principal focus over here. Now I'll start drawing this second line. It's supposed to be parallel to the principal axis once it emerges from the object. So here I have my parallel line. And the point where it converges, it meets the first line is the point where the object is located. So here I have my object, the two lines, and they are converging at point I. 3. Using figure 5.1, determine the distance of object O from the center of the lens. So this is the center of the lens. We have 1, 2, and 2.2, 4, 6, and 7, since this is halfway between the two units. So this is 2.7 centimeters. Question number 6. The speed of sound in air is 340 meters per second. A. Calculate the range of wavelengths for sounds that are audible for a healthy human ear. So the range of sound, the range of frequency which is audible is 20 hertz to 20 kilohertz. And to calculate the wavelength, the formula is speed over frequency. So it's supposed to be 340 divided by 20, which is the minimum value is 17 meters, to the highest value which can be heard is of wavelength speed 340 divided by 20 kilohertz. The highest audible frequency is equal to 0.017 meters. These sound waves are longitudinal waves. Describe how longitudinal waves differs from a transverse wave. So of course, two of the points are going to be definitions of each, and then we're supposed to be writing an extra line, an extra point for longitudinal waves. So here I have the 2 points for longitudinal waves. The last point is See, figure 6.1 shows a band in front of a building. The drum produces a low frequency sound, which means, in other words, a high wavelength sound. Other musical instruments produce a high frequency sound or short wavelength sound. These sounds are equally loud, which means they have the equal amplitude. A young man at the side of the building hears the drum but not the high frequency sounds from the other musical instruments. Explain why this happens. So, the larger the wavelength, the farther a sound wave travels. And since the drum has a low frequency, or in other words, high wavelength sound, it's going to be traveling much farther than the sounds which have shorter wavelength and high frequency. So for the sound to be heard by this other guy which is standing in other direction, the sound has to have enough energy to spread out from the side of the building to the other side. And instead of using the term spreading, we're supposed to be using diffraction over here. Drum has high wavelength sound. Instead of saying spreading, I'm going to be using the term diffraction. So it diffracts more. And that's it. Question number 7. An electromagnet consists of a solenoid X that is made of copper wire. The solenoid contains an iron core. A. Explain why the structure of copper makes it a suitable material for the wire. So we're supposed to be mentioning 2 points for the 2 marks. First, the reason is that it is a good conductor. And then the reason 2. Iron is a suitable material for the core of an electromagnet. Explain why this is so. Similarly, here we're also supposed to be writing 2 points. B. Figure 7.1 shows the electromagnet inside a second coil Y. Second coil Y. 1. Describe and explain what happens in solenoid Y when solenoid X is connected to an alternating current power supply. Alright, so once alternating current power supply is switched on, the a magnetic field is produced in the coil because of the AC current, and due to that magnetic field, um, the iron core is magnetized, and the magnetic field of iron core is going to be much stronger than the magnetic field of solenoid X. So since this magnetic field in iron core is induced by an AC current, which means the magnetic field is going to be changing. Due to that changing magnetic field, when it is cut by um, these turns of solenoid Y, an EMF in turn is produced in solenoid Y. And that is the explanation we're supposed to be writing over here. alternating magnetic field is produced in X. Or this is supposed to be alternating because AC current has a changing directions, and due to this alternating magnetic field, when it is cut by the turns of solenoid Y by electromagnetic induction and EMF is induced in Y, two, a switch and a lamp are connected in series with the terminals of solenoid Y. When the switch is closed, the lamp lights up at normal brightness. Describe and explain what happens to the current in solenoid X when the switch is closed. Alright. Since we had a changing magnetic field in a solenoid X over here, that means an alternating current is going to be induced in a solenoid Y, which means the voltage of the current is the voltage over here is going to be deflecting or fluctuating. And despite the fact that the voltage increases and decreases, the question over here states that when the switch is closed, lamp lights up at normal brightness. Brightness is dependent on power, which is equal to voltage into current. So if the voltage due to alternating current decreases, what do you need to have? You need to have the current sufficient enough for it for the lamp to light up at normal brightness. So if the voltage does decrease, the effect is nullified by the high amount of current over here, and that is why the power, which means the brightness of the lamp, does not have any effect. So the current over here increases. Once again, the brightness depends on the power, and power is dependent on voltage and current. The voltage over here, since it is induced by a changing magnetic field, it's supposed to be an AC current, and due to that the voltage in AC current increases and decreases, it fluctuates, and despite the fact that it fluctuates, the lamp lights up at normal brightness, and that means the current has to be high enough for it to have enough power to be lighting up at normal brightness. And so this is the question number 8. The power supply used in an electrical vehicle contains 990 rechargeable cells, each of electromotive force 1.2, which means 990 cells multiplied by 1.5 have the total electromotive force of 1188 volts. The cells are contained in packs in which all cells are in series with each other. So the fact that it's mentioned over here they are in series, that should mean that the voltage is divided but the current in each of the cell is going to be the same. The EMF of each pack is 54 volts. A, calculate the number of packs in the power supply. So this is going to be the total voltage divided by voltage of each pack, and so the number of packs is 22. B, when in use, each pack supplies a current of 3.5 amperes. 1, calculate the rate at which each cell is transferring chemical energy to electrical energy. So the rate is power or which is also energy divided by time, but over here power is equal to voltage into current. The voltage of each cell is 1.2, and as mentioned over here, the cells are in series, which means each cell gets the equal current of 3.5, and that is equal to 4.2 watts. 2. The packs are connected in parallel to supply a large current to drive the electrical vehicle. Explain why it is necessary to use thick wires to carry this current. So cross-sectional area and resistance are inversely proportional, which means thick wires with a greater cross-sectional area would give less resistance. So thick wires have low resistance, which means less heat is generated. And also less thermal energy is lost. And this makes the wires more efficient. 9a. Describe how a digital signal differs from an analog signal. You may draw a diagram. I'll just go with writing their definitions. So digital signals have high and low values only. However, analog signals keep changing. B1. In the appropriate box, draw the symbol for an AND gate and the symbol for an OR gate. So we have the two symbols over here. It's supposed to be a curved line. And that's it. 2. State how the behavior of an AND gate differs from that of an OR gate. So AND gate only has the output as 1 when both the inputs are 1. However, OR has 3 outputs as 1, and the only case where the output is 0 is when both of the inputs are 0. C. An arrangement of logic gates A, B, and C is shown in figure 9.1. The arrangement has two inputs X and Y and two outputs P and Q. Output P of logic gate B has logic state 1 or high. 1. Determine the logic states of the two inputs of logic gate B. Since this is a NOR gate, it means it is going to be an exact opposite of an OR gate. Alright, so P over here, output P over here is 1, which means since this is a NOR gate, the opposite of an OR gate, it only has the output as 1 when both of the inputs are 0 and 0, and that means upper and lower inputs are 0. Determine and explain the logic state of output Q. I'll start by labeling the inputs over here. This is a 0 and this is also a 0. Right, this is a NAND gate, which means an opposite of an AND gate. So if the NAND gate has the result 0, the only case that it is going to be 0 is when it has both of the inputs as 1, because this is the exact opposite of an AND gate. And that means this lower input is going to be 1, and those two are 1. And since the upper input of Q is coming from Y, this is 0. So 1 and 0 in case of a NOR gate, which is opposite of OR, give the answer as 0, because OR would have given in this case the output as 1, but since this is the opposite of OR, this is going to be equal to 0. And we're supposed to be explaining this, where we have to mention all of the inputs and outputs. So the two inputs in NAND gate are 1, lower input to C, which means this one derived from X, is also 1. So output Q is going to be equal to 0. Question number 10. Figure 10.1 represents a neutral atom of an isotope of element X. A. State one similarity between this atom and the neutral atom of a different isotope of element X. The only difference would be number of neutrons, which means number of protons and neutrons are going to be the same. You can write either of them. B. The isotope of element X is radioactive. It decays to form an isotope of element Y by emitting a beta particle. 1. Using figure 10.1, reduce the nuclide notation for the isotope of Y produced by this decay. Alright, so here we have 5 protons and 1, 2, 3, 4, 5, 6, 7, 8 neutrons, which means the mass number is going to be equal to 8 plus 5. So X had the nuclide notation as 5, which is the mass number, plus 8, which gives the answer as 13. And since this is going to be a beta radiation, the new isotope is supposed to have the same mass number, but the number of the atomic number is going to increase by 1, which means 13 is the mass number and atomic number is 6 over here. 2 beta particles ionize the air as they pass through less strongly than the same number of alpha particles. Suggest why this is so. So alpha particles is basically 2 protons and 2 neutrons, which means this alpha particles has a higher charge than beta particles, which has only a charge of -1. So 2 plus are greater than 1 minus, and so they also have a heavier mass because protons are heavier than electrons, and also alpha particles have 2 protons and 2 neutrons, which makes it much heavier. They have a greater charge, heavier mass, and also greater energy due to their greater mass. So I'll start by the description of beta particles over here. So beta particles That's it. Thank you for watching.